everyone. My name is Siyuan. I will keep the talk short since we are going to have lunch. So today I'm going to talk about one of my recent work that I did during my PhD, and it was published this year in Quantum Science and Technology. So it's about using dynamical decoupling to suppress crosstalk for multi-qubit quantum system. This is the outline of the talk. So since we are dealing with errors, first I will just introduce some common methods for error mitigation and error suppression. And then I will introduce the concept of dynamical decoupling and introduce our proposed staggered DD protocol. And then I will show some results for two experimental settings, the idle-idle experiment and driven idle experiment. And finally, I will discuss and conclude. So here is a nice figure to show the framework of error mitigation. So if there is no error, we will just get our noise-free expectation value C theta. But we know that noise exists in the quantum hardware, so we will get this noisy expectation value C tilde theta. If we want to do error mitigation, so for example, we can prepare different initial states, or we can change the implementation of the circuits, change the measurement basis, or we introduce some ancillary qubits. So basically, we will prepare the circuit in different versions, and then we measure them, use some post-processing method to derive the error-mitigated expectation value. Some examples are zero noise extrapolation or probabilistic error cancellation. And also the error mitigation is done on the software side. On the other hand, we have error suppression, which tries to handle errors at the closest level to the hardware. So we try to anticipate what hardware errors are, and then we try to correct them at the hardware level. So some examples are pulse scaling or dynamical decoupling. The benefits for error suppression is that it does not need quantum resource overhead. And the focus is dynamical decoupling. And first, let me briefly introduce the concept. It tries to suppress the decoherence error by reducing the interaction between the system and the environment. So here's an example. We have a single qubit quantum system. So during the idle period, it has some interaction with the environment, so the system will lose its information. Then we can try to insert some DD sequence during the idle period. They are implemented into some single qubit gates, and then it can reduce the interaction to protect the quantum system. And here's the example of how to insert DD to a quantum circuit. We have a 3-qubit quantum circuit. Before we execute it on the quantum hardware, we need to schedule the circuit, so some delay are inserted, and then we insert X2 DD sequence. So here's just an example. We have many different DD sequences that we can choose to insert during the idle period. Here's just an explanation about how a YDD can suppress the decoherence error. So the idea is that by inserting DD sequence, the unitary of the Hamiltonian for the system-based interaction will become like identity so that it can reduce this error. In our paper, we try to use DD to suppress crosstalk. Since we are doing our experiments on IBM device, so our focus is on the crosstalk for IBM device. But crosstalk also exists in many other quantum platforms like trapped ion, neutral atoms, etc. And in IBM quantum device, it has two types of crosstalk. First one is the static ZZ crosstalk, which exists between the coupled qubits, like Q0, Q1, Q1, Q2 here. And then it also has this driven crosstalk, which means if we have a CNOT gate here, it will introduce the crosstalk to the feeder qubits, Q2, Q3, and vice versa. So we have these two types of crosstalks. We want to handle them. But if we use the standard DD sequence, we cannot handle this crosstalk well. And let me explain why. So let's say we have a 2-qubit quantum system, and we insert the standard X2 DD sequence. So this 2-qubit system goes through an idle period of 2 tau. And first, it goes through an idle period of tau over 2. We insert the first X gate. it goes through the other idle period tau, the second X gate, and then another idle time tau over 2. And also the two X gates are the same on the 2 qubits. During the idle period, we have ZZ crosstalk. It can be modeled using this ZZ gate. And theta is equal to the idle time duration times the ZZ coupling rate between the 2 qubits, which we can obtain from IBM calibration data. We can see this since ZXX happen at the same time, and they commute with ZZ, so this ZZ crosstalk will accumulate across time. So this standard X2 DD sequence cannot address crosstalk. But in our paper, we propose a very simple solution. We change the location of the X2 gates on the second qubit, so they stagger with each other. Now we do not have simultaneous the XX anymore. We have XI and IX, which intercommutes with ZZ, so the ZZ crosstalk can be suppressed. So first, we just do some noise simulation to show that our protocol works. We perform this T2 Ramsey experiment, and the oscillation frequency at the beginning is 100 kilohertz. And then we introduce the neighbor qubit Q1 and insert this ZZ crosstalk and the standard DD X2 DD sequence. There is a shift of this oscillation frequency. But if we use our staggered DD protocol, oscillation frequency is almost the same as the original one. So it can show our protocol works. And the second thing we want to do is we want to evaluate them on the real quantum hardware. So first we need to choose different DD sequence to evaluate. For example, we choose X2, XY4, and XY8. There are some common DD sequences. We prepare them in the standard version, staggered version. And since staggered version, the 2 qubits are asymmetric, so we can just switch them. It is called the inverse of the staggered version. And also we prepare the gate in different pulses, this XP and X minus, which it means we have a pi rotation over the X pulses, but the amplitude can be positive or negative. So by implementing this kind of pulse, it can reduce some systematic errors. The next thing we want to do is that what kind of circuits that we use to benchmark our DD protocol. And we choose this randomized benchmarking circuit because it's a very common method to benchmark the gate error for quantum hardware. So here we can see we have this RB circuit with several Clipper sequence, and between each Clipper sequence, we insert the delay, and then during the delay, we insert the different DD sequence. You can see we have the standard X2PM, the staggered X2PM by changing the location of the X gate, and then we switch them. We have this inverse of the staggered DD. The first experiment we do is this idle experiment. We choose 2 qubit pairs that they are neighbors. So the connectivity is shown here. And both of them go through some idle period, and then we insert DD to this idle period. We can see since they are idle at the same time, we call it idle experiment. And the static ZZ crosstalk exists between these neighbor qubits. The second one is this driven idle experiment. For the first qubit pair, it's still the RB circuit, but for the second one, it has this random SU4 gates, which can continuously introduce some driven crosstalk to the first qubit pair. So now we have not only driven crosstalk, but also this static ZZ crosstalk as well. And we call it driven idle experiment. When we execute the circuits on IBM quantum hardware, we need to take care of some hardware configurations. So there are 2 types of CNOTs on IBM quantum device, and one is echo cross resonance, and the other one is direct CNOT gate. And also their hardware has the native gate direction. So if we have 2 qubit pairs, the connected 2 qubits can be control target, or target. So, and we choose a subset of 10 qubits from this 27 qubit quantum device, which contains all these configurations. We prepare the number of Clipper sequence to 8 to ensure a pretty high initial fidelity. And then we insert delay between each Clipper sequence. And then we change the duration of the delay to this range. It seems weird, but it's the multiples of the sampling rate for the waveform generation on IBM quantum device, which is 0.22 nanoseconds. And then we insert DD to this idle period and check the return probability. To quantify the average fidelity across time, we use this average fidelity. Here, F0 is the initial fidelity. So here are some results. Since we have more than 20 DD variants, first I will show this X2PM DD sequence with this variance. We have X2PM, X2PM stagger, and the inverse of X2PM stagger. The x-axis is the duration of the delay between the Clipper sequence, and the y-axis is the return probability to the initial state. If there is no error, it should be 1, but since we have this loss of errors, so it will decay. And compare with this free evolution, which is a black line, we can see all the DD sequence can improve the fidelity. I forgot to mention that first we performed RB circuit with all this DD sequence individually to set up a baseline. And then we perform this simultaneous RB on 2 qubit pairs to compare. And you can find the results for all the other configurations in our paper, the results. We can see this staggered and staggered inverse give us almost the same results. Both of them outperform the standard DD sequence. And then here are the results for XY4 and XY8. XY4 consistently outperform XY8, but in theory, XY8 should perform better because it can correct higher order errors. But based on our experience and some other papers, we can see that the performance of XY8 is really circuit dependent. So maybe for this type of circuit, it is sensitive to the single qubit gate error. Since XY8 has more single qubit gates, it does not perform well. And also, we see some outliers here. It's not unique in our experiments. We also saw the similar behavior in other papers. So there are some complicated noise on the quantum hardware that we are not aware of. Since XY8 outperforms XY4, so for this driven idle experiment, we only show the results for X2 and XY4. And again, both of them outperform the standard DD version. Okay, to conclude, the main takeaway message I want to convey is that DD is one of the simplest error suppression methods and is worth exploring, but it cannot always improve the circuit fidelity. When we put out the paper, there are also some papers from IBM. They are discussing how to implement the strategies of how to insert DD sequence, which DD sequence should we use. So it's an open research problem. And also our staggered DD can reduce the crosstalk compared with the standard DD version. For the future works, we can, for example, apply this staggered DD protocol to some more advanced DD sequence like UDD, concatenated DD, etc. Also, for our experiments, all the idle time are unified. So we can also try to design some scheduling method for non-unified idling time also for large quantum system. Since DD only has this single qubit gate overhead, it is very natural to combine it with, for example, error correction code to see how it can help with this fault-tolerant quantum computing. And then we also need to dig to understand more about the hardware noise and to maybe design some hardware-oriented DD strategy. So that's it on my talk.
I have a circuit with 8 qubits and depth of 10 CNOT gates. Could I use your method to test how it works on my circuit?
Yes, sure. Yeah, you can send it to me and I can try it.
So just a comment, so you could consider, so let's say, so you look at like different DD sequences and you look at the staggering and so on, right? So, at the risk of high computational cost, you could try building like a higher level framework which allows for like different kinds of staggering, different kinds of DD sequences, and say if you're running this on top of like Clifford circuit, so you can try to find the optimum sequence for a Clifford circuit which represents your target circuit on a particular device, right? So
Yes.
we had done some work like this, specifically for like variation algorithms where we are deciding like how to like space.
Yes, I read your
DD
paper about
sequences.
that.
So
Yeah.
but it's kind of limited in that all we care about there is the spacing between DD sequences, but there are many more variables you can use,
Yes.
right? But of course, it's a pretty large optimization space, but
Yeah.
it's maybe a good thing to try on Pearl models.
Great job. You have a figure on its fidelity versus the staggering time, right?
What?
So what's the intuition like behind like the choice of a staggering time?
Because the more idle time you have, the more errors you will get for the decoherence error. So then the fidelity will drop.
So what if I have like a random idle time? That improve the performance or
Around.
a random stochastic choice of staggering time? That
So
have your
the long,
error.
yeah, the longer idle time you have, the worse your fidelity is. That's the intuition.
Thanks.
What was the tooling that you used to do it?
What's the tool?
The tools that you used, did you use Qiskit or Biscuit or
I use Qiskit to do that.
Qiskit?
Yes.
Have you compared the level of error without your technique and with your technique, how much improvement?
Yeah, this is without any. This is with the standard other techniques. And also for this one, we have two experiments. Also, this is the based on where no DD is inserted. This is the art, and this is the.
That's significant.
This phase, especially if you have longer delay.
Hi, I loved your talk. On some level, gates are sort of artificial. On the hardware level, what the qubit sees is pulses. Is there any argument to directly use pulses and do their inverse operation for EV rather than heavily use X-gates or Z-gates staggered?
Yes, so for my experiments, I always use the gate instead of the pulse, but you can always tune your pulse to do these experiments as well.
Believe that there's any ceiling there?
Maybe, but there are also lots of parameters you need to optimize for your pulse, so I'm not sure if it's worth.
Thank you, speaker.